We'll move on to factory tests, and that'll be the last thing we're going to do today.
Okay.
And the first thing in this is called a dielectric test. It says it has a applied voltage without electrical breakdown of a 1 minute 900 volt AC or 1280 volt DC dielectric strength test, or a 1 second 180 volt AC or 1530 volt DC dielectric strength test. What is that for?
Well, it's testing the integrity of the insulation and also the terminations. We usually call it Megger testing, and it's a tester that you can induce a higher amount of voltage and a small amount of current for a short period of time to see if it fails. And if it fails, it doesn't destroy the device. It just tells you that you need to go back and look at what you installed to make sure all terminations are good and the installation is complete.
It also says that that needs to be tested with all the switches closed between the ungrounded and grounded conductor.
Yeah, it has to have a complete path. So if you open the device like a switch, then there is no more complete path. So it needs to make sure everything is on and everything is connected.
Okay, so that's what that means. What's a continuity test?
Continuity test is exactly like we was talking about metal framing. You can go from one metal frame to another. It should be very low amount of resistance, if any. The only resistance that would be in that continuity test would be the actual composition of the metal that you're using on the resistance of length. Like a conductor is rated in ohms. That's why we have voltage drops. If you use a conductor for a very long distance, it's not about the size of the conductor, it's about the length of the conductor. And the longer it is, the more resistance there is in the conductor. It's just a natural part of the construction of the conductor. So continuity test is about making sure that everything is securely bonded and is what I call is an equal potential grounding. It's the same no matter where you go.
Okay, and then an operational test is just turning on the equipment.
Turning on the switches. Does it work? Does it go on and off?
Okay.
Yeah.
All right. What's a polarity check?
Polarity check is all the receptacles, like we were talking earlier, are NEMA rated, or National Electrical Manufacturers Association, and they're UL listed. And you'll look on the device, it's going to have a white colored screws on one side. Normally, if you're looking at the device and it's facing you, it's on the left-hand side. And on the right-hand side of the device will be a brass colored. And then you're going to have a green colored screw on the yoke or the metal frame. With that being done, the black goes to the dark colored screw, brass. The white goes to the white colored screw, and the green goes to the green, or the bare goes to the green. That polarity will show on a tester when you energize that circuit and it's connected properly and it's properly colored, that will show you a polarity of correct. If it's incorrect, it's going to usually tell you what is missing. The equipment grounding conductor, you forgot to connect it, or somewhere it's loose, or the connection wasn't good, or if it's a neutral conductor, or it won't show anything if you do not have the ungrounded conductor connected properly, because there's no energy there for it to measure. So the polarity is to make sure that you got white with white, and green and bare with green and bare, and the black with black.
Okay.
Or in this sense of the word, I'm using black as a universal color. It could be red, blue, pink, turquoise, all kinds of different colors. Normally,
just not
black
green.
or red.
Just not a green color.
No, just not a green, not a white.
Not a white. Okay. All right. What's a GF? You talked a little bit about a GFIC.
Yeah, ground fault interrupter circuit. And if you look in the definitions in the code book, everybody is going to do something like this, they should have a code book or contact NOAA and make sure a ground fault circuit interrupter, which I read earlier, is the device that is intended for the protection of the personnel. I can stop right there because it is looking at, before I said what goes in must come out. In other words, if a conductor is connected properly, whatever the load may be, a light bulb or a dishwasher or a piece of equipment, whatever goes in current level should come out the same. In other words, if I put an amp probe, which is a measuring device to measure current flow, then I can clamp on that black conductor, and let's say it's 5 amps. If I clamp it on the white, it should be 5 amps. If I got black conductor 5 amps and 3 amps on the white conductor, it's lost it somewhere. So it's grounded somewhere. And a ground fault circuit interrupter is looking for that imbalance. So if you plug in a device and there is an imbalance in it, it's going to trip that device to where it de-energizes that, so no one gets electrocuted, because it doesn't know if it's the device failing, the piece of equipment that you got plugged in, like a cord with a frayed a conductor on it outside. There's an imbalance. It's thinking, and it's designed to trip on an imbalance, because if it's an imbalance, that may be you, and you may be having electricity traveling through your body, so therefore you're being electrocuted. It's going to try to stop that within milliseconds, and it only allows 5 milliamps, which is a very small amount. So all you feel is, wow, it tripped right away, my equipment doesn't work. Well, you need to find out why it doesn't work. Usually it's equipment, or faulty piece of equipment, or the device is failing. So a ground fault circuit interrupter is there to look at the imbalance of current flow going in and out. And if there is one, and it's more than 5 milliamps, it will disengage or de-energize that device.
So when we're talking about testing a GFIC outlet, there is a thing you can buy at Home Depot, Lowe's, or an electrical supply store that will check polarity and ground fault interrupter circuits. It's not very expensive, but how does that? It's a little.
It's all based on Ohm's law, and Georg Ohms a long time ago figured out how electricity operates and the different potentials that it provides. And with that being said, we primarily have 3 elements when we conduct electricity. We have the resistance, and we have the current, and we have the voltage. The voltage is like water pressure. How much pressure you have on that line determines on the voltage level. And then current has to do with the flow, like water flow in a water pipe. And then resistance has to do like elbows or anything that resists the flow of water. In this case, we're talking about electricity. So what it's doing is it allows you to plug in a device. It has a little resistor in there rated at a certain ohm value. So when it's on a 120 volt circuit and it's a certain ohm value, within Ohm law comes out to be 0.5 milliamps, 0.05. So with that being said, if it exceeds 5 milliamps, which that resistor is designed to do, you push that little button that says test. It allows that to have that difference of current flowing through that device, and it will trip it. So the device should trip itself. It's showing you that there is an imbalance and the device is doing what it's designed to do. That's what a GFCI tester, polarity test, well, not polarity tester, but GFCI tester does. It checks the imbalance and it will trip the device, and you know it's working fine. You reset it, then you try it again, or you can manually test reset. So you're mechanically checking the device and you're electrically checking the device that it is doing its job and it's safe and for use.
So you can have the same tester that you buy can test polarity and the ground fault.
Yes, it can. You can go to a regular receptacle and do the same thing. If you push the button, it's not going to do anything because you don't have a ground fault device hooked on that circuit.
Okay. Well, let's talk about arc fault a little bit. I don't see any arc fault breakers being used in tiny houses.
No.
And there hasn't been anything in the Article 551 about arc fault. Do we need to have arc fault in there, or what's the reason?
Well, what I think that the correlating committees, in the National Electrical Code, there's committees formed, and these people are from all different fields in electrical, some engineers, some electricians, some inspectors, some fire marshals, some insurance inspectors. So they get a group of people together, they assign them a part of an article, and to make a long story short, there was a committee formed for arc fault interrupters. Primarily, GFC, as I talked about the imbalance, and that pretty well makes sense, and it protects you from getting electrocuted. But arc fault does a little step above. A lot of people love to run extension cords. They do it all the time. Well, now they're running them on the rugs, or they're running them to where there's a chair leg sitting on that cord. Well, a GFCI is not going to detect that, because if you have a short in the GFCI, you'll burn that receptacle up. But if you have an imbalance, it'll trip it. So it's designed to trip an imbalance to protect you from getting electrocuted. An arc fault is designed to be used to where if you set something on the cord and it arcs, which an arc is an intense heat flame that causes combustible items to catch on fire, it is sensing that arc immediately, tripping that circuit before it becomes such an arc to be able to ignite a combustible item like material, rug, wood, whatever that may be. So if you didn't have that arc fault, a breaker works on inverse time. As current goes up, time shortens, breaker trips. That could be too long of a time for a direct short on a cord. You already have the fire, but the breaker trip, well, it's too late. It's already started to fire. An arc fault conduct or protector, breaker, receptacle, whatever that may be, is designed to keep an arc from happening to cause a fire. They find that's normally in bedroom areas. They're plugging in maybe heating pads, or they're plugging in something, electric blankets or something like that, and the dog's chewing on it at night. They're trying to keep things from happening before they actually cause damage. So they use different things. Circuit breaker to protect the conductors, a ground fault interrupter to protect an imbalance from you getting electrocuted from what locations, arc fault to stop an arc immediately before it causes enough intense heat to ignite a combustible item, which would cause a fire and burn the house and take life. Does that make sense?
It does. That's very clear.
Okay.
You did a good job of explaining that. Well, that's about it for today. Want to thank you, Gary, for
You're
coming
welcome.
out and sharing your knowledge with us. Vast resource there, obviously, more than we could go over in a short period of time that we have here. But if you guys are interested in anything further, you can certainly go to noaacertified.org and find out a little bit more information. And we will go ahead and close out this this session right here.